Good morning everyone. Today we will discuss about switched capacitor circuits. Till date we have dealt with the circuits where the input signal is continuously available and applied to the circuit and output signal is also continuously observed. These circuits are called as continuous time circuits. Such type of circuits, for example amplifiers, find wide applications in audio, video and high-speed analog systems. However, there are many situations in which we may sense the input only at periodic instants of time, while ignoring its value at other times. The circuit then processes each sample and produces a valid output at the end of each period. Such circuits are called discrete time or sampled data systems. So today we will discuss about this kind of discrete time systems called as SC or switch capacitor circuits. This lecture is basically to provide the foundation for more advanced topics such as filters, comparators, ADCs and DACs. In order to understand the motivation for sample data circuits, let us first consider simple continuous time amplifier as shown in the figure A. This is used extensively with the bipolar op-amps. This circuit presents a difficult issue if implemented in CMOS technology. Recall that to achieve a high voltage gain, the open loop output resistance of CMOS op-amps is maximized. Typically, it approaches hundreds of kilo ohms. We therefore suspect that R2, that is a feedback resistor, heavily drops the open loop gain. Thus, it degrades the precision of the circuit. In fact, with the aid of simple equivalent circuit, which is shown at the right hand side figure B, we can write the simple equation for Vout upon Vin as minus R2 by R1 into AV minus Rout upon R2 divided by 1 plus Rout by R1 plus AV plus R2 by R1. If you observe this equation carefully, it implies that the closed loop gain suffers from the inaccuracies in the numerator as well as denominator. Also, the input resistance of this amplifier, that is R1, lowers the preceding stage while introducing the thermal noise. The closed loop gain is set basically by the ratio of feedback resistance, that is R2, and the input resistance, that is R1. In order to avoid the reducing the open loop gain of the op-amp, we postulate that the resistors can be replaced by capacitors. So this figure from the left hand side is the same type of amplifier, but we have replaced resistances by the capacitances. Now if you replace the resistors by the capacitors, now the problem is how do you set the bias voltage at node X? So to set the bias voltage at node X, we can add a large feedback resistor, which is shown in another figure towards right hand side. This feedback resistor provides the DC feedback while it negligibly affects the AC behavior of the amplifier in the frequency band of interest. Such an arrangement is indeed practical if the circuit senses only high frequency signals. But suppose, for example, the circuit is to amplify voltage step, which is shown in the right hand side figure. The response contains a step change due to initial amplification by the circuit consisting of C1, C2 and the op-amp, followed by tail resulting from the loss of charge on C2 to the feedback resistor RF. From another perspective, we can say that this circuit is not suitable to amplify the wideband signals because it exhibits a high-pass transfer function. We can write the transfer function for this network, that is V out by V in a function of S is nearly equal to minus total feedback impedance, that is ZF, divided by the input impedance, that is Z1. So ZF is nothing but parallel combination of RF and C2. Therefore we can write it as RF into 1 by C2S upon RF plus 1 by C2S, and Z1 is nothing but the capacitor C1. Therefore this is divided by 1 by C1S. So when you simplify it, you get minus RF C1S upon 1 plus RF C2S. Thus, if frequency, that is omega, is very large as compared to 1 by RF C2, then obviously this equation can be approximated at minus C1 by C2. Thus, this difficulty, that is, we can use it only for the wideband signals when frequency is very high, can be remedied by increasing the RF C2. But in many applications, the required values of the two components become prohibitively very large. We must therefore seek other methods of establishing the bias while utilizing the capacitive feedback. So before solving the issue, let us try to solve this simple numerical. What it says is that for the given circuit, op-amp is characterized by transconductance capital GM and an output resistance R out. So part A is determine the transfer function V out by V in this mode, and part B is plot the waveform at node B if input is 100 MHz, sinusoid with a peak amplitude of 1 volts, C1 is equal to 1 picofarad, GM is 1 upon 100 ohms, and R out is equal to 20 kilo ohms. So this is the solution wherein circuit is redrawn. Now we replace this op-amp by an equivalent circuit, that is Vx is the input voltage, differential input voltage, and output is now transconductance capital GM times Vx. The input voltage gets converted into an output current. C1 is the input capacitance and R out is the output resistance. We have to find out V out by V in. Thus, we can find out the impedance at the output side, total impedance. Thus, this current is the current source with its impedance as 1 by GM. So, this 1 by GM will be in parallel with R out, and there is C1S. So, we can write impedance V out by V in as 1 by GM parallel to R out into C1S upon 1 by GM parallel to R out C1S plus 1. So simplify this, you will get the equation as 1 upon GM C1S upon C1S by GM plus 1. So this is the part A, that is we have to determine the transfer function, and we got it. Now the part 2 is we have to plot the waveform for a given input of 100 MHz. C1, GM and R out is given. Thus, we substitute omega, that is 2 pi f, C1 as 1 picofarad, 1 by GM is 100 ohms into this equation, and we get C1 by C2, C1 by GM into omega as 0.0628. Therefore, V out by V in we get from this equation as 0.0628. Thus, we can draw input and output waveform. Output waveform will have an amplitude of 0.0628 than that of input, and there will be a phase shift of 90 degrees because it's an RC network. Now let us try to focus on the issue that we have discussed earlier, that is, to have a wideband amplifier we have to increase RFC1, which is not a practical solution. Thus, is it possible to replace this RF by some other components? So let us consider this network in which we have shown an operational amplifier along with capacitors C1, C2, and there are some switches to control the operation. S1 and S3 connect left plate of the capacitor C1 to Vin and ground respectively, and S2 provides unity gain feedback. We first assume the open loop gain of op-amp is very large, and let us study this circuit into two phases. So in first case, let us say S1 and S2 are on and S3 is off. So this gives us an equivalent circuit which is shown in figure A. So for high gain op-amp, VB is equal to Vout, which will be equal to 0 because of the virtual ground, and hence the voltage across capacitor C1 is approximately equal to input voltage Vin, which is shown in this figure. Thus Vin is a sine wave, Va follows Vin, but Vout will be equal to 0 till time t equal to 0. Now next, at time t equal to 0, S1 and S2 let us turn off and S3 is turned on. So this pulls the node A to the ground, which is shown in figure B. Since Va changes from Vin 0 to 0, the output voltage must change from 0 to Vin 0 C1 by C2. The output voltage change can also be calculated by examining the transfer of charge. That means the charge stored on C1 just before T0 is equal to voltage into capacitance, that is V in 0 into C1. After T is equal to T0, the negative feedback through C2 drives the op-amp into a differential voltage, and hence the voltage across C1 to 0. The charge stored on C1 at T equal to 0 must be transferred to C2, which produces an output voltage equal to V in 0 C1 by C2. Thus, we can say that the circuit amplifies the input voltage, that is V in 0, by a factor C1 by C2. What this circuit distinguishes from the continuous implementation is that the circuit devotes some time to sample the input, setting the output to 0, and then provides no amplification in this period, while there is a second phase, that is after t equal to 0 or after t0, the circuit ignores the input voltage V and it simply amplifies the sampled voltage. Thus, we get a switch capacitor implementation in which we can say that the circuit first samples the input and then we get the amplification. So this is a simplified version of any switch capacitor circuit, any switch capacitor implementation, which shows that first there is a sampling period and then there will be an amplification period. Thus we need switches for implementation of the switch capacitor circuits. So what are the kinds of switches that we can use? Let us consider the topmost figure, that is V input is there is a switch and then there is a capacitor. So this switch is nothing but an NMOS transistor. It is driven through the clock. And this middle figure shows that when the input is high, then what will happen? So this switch acts as a resistor, the switch is on, and whatever is the input, it will be transferred at the output. While when switch is low, whatever is the input, output will be 0. This is our preliminary discussion. Now let us discuss this in detail. One of the best advantage of MOSFET as a switch is that it can be on while carrying zero current, which we have discussed in earlier lectures. That is, MOSFET switch carries a zero current, but you call that switch is on. One more advantage it has is that its source and drain voltages are not pinned to the gate voltage. That is, if the gate voltage varies, the source or drain voltage need not follow the variation in the gate voltage. These two properties are not there in the bipolar transistors, and hence we go for MOSFET as the switches. Now let us consider this figure in which we are applying input as 0 and output is assumed that it has been charged to VDD. Therefore, when you switch on the switch, then all the charges from the capacitor CH will be grounded towards input side. Therefore, output voltage drops from VDD to 0. So in this case, gate voltage is CK and the source voltage is 0. So VGS remains as it is and switch remains turned on. Now let us say you apply input as plus 1 volt, which is less than your VDD, and you also switch on the switch by applying the clock, and initially capacitor is not charged or voltage across the capacitor is 0 volts, which is shown in the right hand side figure. So now when you switch on the switch, then the capacitor will start charging and obviously it will reach to maximum value plus 1 volt. Now let us say you increase the input to the maximum value, that is VDD. Now when you switch on the switch, then capacitor will start charging. However, in this case, gate voltage is clock and the source voltage is V out. Thus, source potential keeps on continuously changing. That means VGS continuously changes. VGS basically drops. So, when output voltage reaches VDD minus VTH, VGS will be equal to threshold voltage. After that, VGS will be less than VT. Therefore, switch turns off when output voltage reaches VDD minus VTH. Therefore, maximum output possible in this case is VDD minus VTH and output does not reach to VDD. Thus, we can say that for V output to be nearly equal to V in, transistor must operate in a deep triode region, which is shown in the middle figure by a resistor, wherein output voltage will follow the changes in the input voltage. So this input voltage that you apply has an upper bound and it must be limited to a maximum value of VDD minus VTH. If you apply input voltage more than VDD minus VTH, then it will be clipped, or you can say switch will be turned off. So these are the numericals which you can solve. How does V out vary with time if V input is 0? Assume lambda equal to 0. So in the earlier PPT, we have already got these plots. So that is the answer. Then for next case also, when V input is 1 volt, what is the V out? So it will charge to 1 volt. So that also we have solved. Now let us try to solve the another numerical. Calculate the maximum, minimum and the maximum on resistance of M1. So to calculate the resistance for the switch shown that is M1 in the figure. Also mention what is the maximum on resistance if the input level is raised to 1.5 volts. Thus in first case input is 0.5 volts, and in second case you have to increase the input to 1.5 volts, and then you have to calculate the maximum on resistance. Rest of the parameters are given. So what is the formula for the on resistance? On resistance is nothing but 1 upon mu n C naught x W by L VDD minus V in minus VTH. So this formula we will use over here. So everything is given, that is mu n C naught x W by L VDD VTH is given. Now in first case you consider the V in as 0.5 volts, substitute the values and calculate. So M1 remains in the triode region because the gate voltage is higher than V in, and V out by value greater than VTH. That means we predict that V out tracks the V input with a negligible phase shift due to the on resistance of M1 and CH. So if you substitute the values over here for V in 0 and V in 0.5, we will get the maximum on resistance as 1.11 kilo ohms and the minimum on resistance at 870 ohms. Now you increase the input to 1.5 volts, that is you substitute in this formula V in as 1.5 volts and calculate the on resistance. So now you will get the answer as 2.5 kilo ohms. What does it mean? When input voltage is 0, you get the on resistance as 870 ohms. When input voltage is 0.5 volts, you get on resistance as 1.11 kilo ohms, and when input voltage is again increased, then you get on resistance as 2.5 kilo ohms. So what is the conclusion from this numerical? The conclusion is that the resistance of the switch, it depends on the input voltage in case of NMOS device. Now for this given circuit, assume W by L of 1 as 20 by 0.5 and CH as 1 picofarad. Calculate the time required for V out to reach to 2.1 volts. Thus we have to find out the time required for the output voltage to reach to 2.1 volts. Now for this circuit, we have to derive the equation for the output voltage. You cannot write directly at V out as VDD minus VTH. So consider the circuit in which gate and drain are at the same potential. That means V in is equal to VDD and Ck is also equal to VDD. That means the transistor is saturated. Thus we can write the equation as Ch dV out by dt is equal to the drain current ID. That is ID is equal to C dV by dt. So ID1 is equal to Ch dV out by dt. And since this is saturated, therefore we can write the equation of saturation, that is 1 by 2 mu n C naught x W by L VDD minus V out minus VTH square. We neglect channel length modulation, etc. And since there is a derivative term, we will integrate it and we solve it. So I left it to the user to solve that derivation. So finally you get a V output voltage is equal to VDD minus VTH minus you will also get one more term, that is 1 by 2 mu n C naught x CH into W by T plus 1 upon VDD minus VTH. This derivation is very well given in the Razavi. You can refer that, and you use that equation to solve this numerical. Thus, in this case, the equation in V out is equal to, so V out is 2.1 given. So you can substitute here 2.1 is equal to VDD minus VTH. So you can have it is 2.3 volts minus 1 upon 1 by 2 mobility mu n C naught x upon CH W by T plus 1 by VDD minus VTH, which is 2.3. Now in this case, everything is known except T. So if you solve it, you will get T is nearly equal to 1.16 nanoseconds. Thus, what we have discussed is that there is a serious limitation of the MOS switches. If the input signal level is close to VDD, then the output provided by the NMOS switch cannot track the input. From another point of view, the on resistance of the switch increases considerably as the input and output voltage approaches VDD minus VTH. Thus, we can ask that what is the maximum input level that the switch can pass to the output faithfully? It is nothing but VDD minus VTH. Thus, the MOS devices operating in deep triode region are sometimes also called as zero offset switches, to emphasize that they exhibit no DC shift between input and output voltages of the simple sampling circuit. Similarly, PMOS transistors fails to operate as a zero offset switch if its gate is grounded and drain terminal senses an input voltage of VTHP or less. In other words, on resistance of the device rises rapidly as the input output levels drops to VTP above the ground in case of PMOS devices. So now let us consider the two aspects. One is called as speed, another is called as precision. So what determines the speed of the sampling circuit? So for that purpose, let us first define the speed. So speed is a versatile measure, and it is nothing but the time required for the output voltage to go from 0 to the maximum input level after the switch turns on. So what is speed? Speed is nothing but the time required for the output voltage to grow from 0 to the maximum input level after the switch turns on. Since the output voltage would take infinite time to become equal to input, we may consider that the output settles within a particular error band, that is nothing but delta V, which is shown in this figure. For example, we say that the output settles to 0.1% accuracy after Ts seconds, meaning that delta V by V in is equal to 0.1%. Thus, speed specification must be accompanied with an accuracy specification. Note that after T is equal to Ts, we can consider the source and drain voltages to be approximately equal. Thus, the sampling speed is given by two factors: on resistance of the switch and the value of the sampling capacitor. Thus, to achieve a higher speed, a large aspect ratio and a small capacitor must be used. However, as we have noted earlier, that on resistance also depends on the input level, which yields a greater time constant for more positive value of the input. So let us plot the on resistance for the NMOS switch. So this is the plot for R on versus input. When input is 0, R on is shown somewhere over here. When you go on increasing the input voltage, on resistance of NMOS switch also goes on increasing, and when input voltage is near to VDD minus VTH, after which switch turns off, therefore on resistance is very large, it is infinite. So this right hand side figure is for the PMOS device. When input voltage is very less, that is less than mod of threshold voltage of the PMOS, so device is off, that means on resistance is very large. When input voltage is greater than mod of threshold voltage of the PMOS, the device is on and hence the resistance decreases. So when you go on increasing the input voltage, then the on resistance of the device will also go on reducing. So now how to solve this problem? So what we do is we can connect one NMOS switch in parallel with the PMOS switch. So if you consider their resistances, they are in parallel, therefore the equivalent resistance will be R-on resistance of NMOS in parallel to R-on resistance of PMOS. So what is R-on resistance of NMOS? It is 1 upon mu n C naught x W by L of NMOS into VGS, that is VDD minus Vin, assuming that clock is VDD, minus threshold voltage. And what is on resistance of PMOS? It is 1 upon mu P C naught x W by L of P into VGS, that is Vin, minus mod of VTP. Correct? VGS is Vin because clock will be inverted. So you simplify this, you will get this equation. Here interestingly, if mu n C naught x W by L of n is equal to mu P C naught x W by L of P, there is this factor, then you can see that there is no V in, this factor will be 0. So R on equivalent is independent of the input level. Thus, if you plot the total resistance now, so you can see that, so it is relatively independent. R on line is relatively straight as compared to R on P and R on N. For high-speed input signals, it is critical that NMOS and PMOS switches in this case turns on simultaneously. However, if both the switches they do not turn on simultaneously, then you may get a negative pedestal in the output, which is shown in the right hand side figure. This network is nothing but a transmission gate. Thus, we can use transmission gate as a switch in the switch capacitor circuits. If you use transmission gate as a switch, what we get is that on resistance of the switch now will be independent of input voltage. Now since R on will be fixed, CH is the capacitor that is fixed, tau is the time constant which is R into C, so RR into CH, that means time constant will be fixed, that is frequency is fixed, hence we can say that speed can be easily identified and fixed for this circuit, which is not true for the NMOS or PMOS switch because R on will go on continuously changing. And in this case, one more interesting thing is that V output will be exactly same as input. So there is no upper bound limit which was there in the earlier case. So the problem is only one, that is if both the switches do not turn on and off simultaneously, then there will be a distortion in the output. So this is the sampling network shown, and it is designed with W by L of 1 is 20 by 0.5 and W by L of 2 as 60 by 0.5. CH, the holding capacitor, has got 1 picofarad, and if input is equal to 0, initial value of Vout is plus 3 volts, you have to calculate the time required for output voltage to drop to plus 1 millivolts. So how are you going to solve this? We have to calculate Vout. So what we will do is, we will convert this network into RC equivalent network. So R on resistance of 1, that is M1, we calculate, and that comes out to be 55 ohms. R on resistance of 2 you calculate, that will come out to be 64.3 ohms. CH is given. So that means R on 1 is parallel to R on 2. So total resistance will be 29.6 ohms. So that means this is the total resistance R 29.6 multiplied by the holding capacitance CH, that is 1 picofarad. So you get a tau, time constant, that is 29.6 picoseconds. Thus we know that for this kind of a RC network, V output voltage is equal to VDD e raised to power minus t by tau. Thus in this case, a Vout given right now is 1 millivolts, which is equal to VDD given is 3 volts, e raised to power minus t by tau we have calculated. Thus we get time t as 237 picoseconds. Thus what we have studied is that if we increase the W by L, that is larger the W by L, or we can say smaller the capacitance C, that means smaller will be the time constant RC, we can achieve the higher speed. Now let us see if you want to increase the speed by doing, that is increasing W by L or by reducing the capacitance, then what about the precision? Will it degrade or it improves? Let us try to find out. So basically there are three mechanisms in MOS transistor which introduces error when the switch turns off, and all those three we are going to discuss right now. So first one is the channel charge injection, second is the clock feed through, and third is the KT by C noise. So for creation of the inversion layer, what we do is we apply some gate voltage in NMOS device, right? Then it creates an inversion layer. It attracts those minority charge carriers towards the interface. Once you get an inversion layer, then you apply the drain voltage and you can get the current. Now when you switch off this switch, that is a transistor, then what about those channel charges? We have never discussed about the channel charges, where these charges will go. So they may go to a source side or they may go to a drain side. So when the switch turns off, the total charge in the inversion layer exists through source and drain terminals, and this phenomenon is called as a channel charge injection. So we know that the amount of channel charges are W into L into C naught X into VDD minus Vin minus VTH. So these channel charges QCH will produce delta V, that is QCH by CH, Q by C, that is QCH by CH. So it is WLC dot X VDD minus Vin minus VTH upon CH. Now let us assume that half of the charges goes towards source and half of the charges goes towards drain. So that means delta V is equal to 1 by 2 QCH, that is WLC naught X VDD minus V in minus VTH upon CH. So this half of the charges which goes towards output side, they will produce an output voltage which is delta V. This voltage is nothing but an error voltage, which you can see from the right hand side figure. So this error for an NMOS switch appears as a negative pedestal at the output. Now let us try to find out the output voltage. Now for the worst case, that means all the charges goes towards the output side. Then V output will be equal to obviously input minus this voltage delta V, that is WLC naught X VDD minus V in minus VTH upon CH. Now you simplify this equation. So you get the V in outside common terms. So you get 1 plus WLC naught X by CH minus outside. Then you will have WLC naught X by CH into VDD minus VTH. So VTH equation is known to us, that is VTH is equal to VTH naught plus gamma into bracket square root of 2 phi b plus VSB minus square root of 2 phi b. And in this network, VSB is nothing but input voltage. If you observe here, VSB is nothing but input voltage. Therefore, you can say VBS is equal to minus V in. Thus, V out is equal to, we can say that now V in minus WLC naught X by CH times VDD minus V in minus, you substitute this threshold voltage entire formula over here. Simplify the equation, you finally get this answer. From this answer, what you can say is that input is amplified by factor 1 plus WLC naught X by CH, while there is a DC offset that is also present in the output, which is given by the rest of the term. So in summary, these channel charges primarily contributes to three types of errors in the sampling switches: gain error, DC offset, and nonlinearity. So you can observe from this plot of sampled output versus input voltage, wherein you can see that there is a nonlinearity now introduced into the output, because the line which goes to the center now it has been shifted, and there is a DC offset, and obviously there will be error into the gain. Thus, it is constructive to consider the speed precision trade-off resulting from the charge injection. Now, if you observe the earlier equation for precision, so now if you reduce the capacitance voltage, capacitance value, that is CH, then output voltage will increase. That means error voltage delta V will increase, right? Or in other words, to reduce the error voltage, that is to reduce the delta V, what you have to do is that you have to increase the value of the capacitor. So if you do this, speed is going to degrade. Thus, there is a trade-off between speed and the precision. Hence, what we do is we define the figure of merit for this switch as F is equal to 1 upon tau delta V. So tau is nothing but R on CH. R on is 1 by mu n C naught X W by L VDD minus V in minus VTH, and this CH, and delta V also we know it is WLC naught X by CH VDD minus V in minus VTH. We already calculated this. You multiply these two, what you can see that VDD minus Vin minus VTH gets cancelled, C0 X gets cancelled, then your CH gets cancelled. So finally what remains is mobility mu n, W also gets cancelled, and 1 upon L square. So figure of merit for this circuit is F is equal to mu n by L square. Thus, at first order, trade-off is independent of the switch width and the sampling capacitor. Now let us try to study another mechanism which introduces an error into the output voltage. That is nothing but the clock feed through. Now we feed the clock to the gate and we assume that there is no effect of this clock onto source and drain. However, it is not true because there is an overlap between gate source and drain source. This overlap creates a capacitance called as overlap capacitance COV at source as well as at the drain side. Now let us say COV is the overlap capacitance per unit width. Then this clock will get coupled towards source as well as drain, and it will generate an output voltage delta V, which is equal to the clock voltage VCK times WC0 V upon WCOV plus CH. So if you observe this entire parameter, it is a constant offset in the input-output characteristics. And this also leads to the trade-off between speed and precision. What does it mean? To reduce this error voltage delta V, what you have to do is you have to increase the capacitance CH. So, but if you increase the capacitance CH, speed will degrade. So, in short, clock feed through is the mechanism by which gate clock gets coupled to the source and drain side, introducing an error delta V, which is a constant offset in the input output voltage, and it leads to the trade-off between speed and the precision. The last mechanism is the noise. Now we are using switch as a resistor. It has got an R on which charges a capacitor, and hence it will also give rise to a total RMS noise voltage as square root of kT by C. So what this figure shows is that a similar effect occurs in the sampling circuit. The on resistance of the switch introduces the thermal noise at the output, and when the switch turns off, this noise is stored onto the capacitor along with the instantaneous value of the input. Thus, the voltage at the capacitor will not be equal to Vin, but it will be equal to Vin plus noise voltage Vn. It can be very easily proved that the RMS voltage of the sampled noise in this case is still equal to square root of kT by C. The problem of kT by C noise limits the performance in many high precision applications. So, in order to achieve a low noise, the sampling capacitor must be sufficiently large, thus loading the other circuits and obviously degrading the speed. That is, there is always a speed and precision trade-off. Now, how do we reduce the charge injection, or how to remove the problem of charge injection? So, there are various solutions proposed. Some of the solutions we are going to discuss over here. So, this is the first technique. We postulate here that the charge injected by the main transistor can be removed by the means of the second transistor. So, in this figure, there is a dummy switch shown, which is M2. It is driven by CK bar. It is added to the circuit such that After M1 turns off, this dummy switch M2 is going to turn on. So the channel charge deposited by the M1 on CH will be absorbed by dummy switch M2 to create a channel. Here note that both the source and drain of M2 are connected to the output node. Now how do we ensure that the charge injected by M1, that is delta Q1, is definitely equal to and absorbed by M2, that is delta Q2? Now suppose that half of the channel charge of M1 is injected onto CH, that is delta Q1 is equal to 1 by 2 Wn L1 C0x into Vck minus Vin minus Vth1. Now since what we want is that delta Q2 is equal to W2 L2 C0x Vck minus Vin minus Vth2. What we have to choose is that W2 should be equal to W1 by 2, that is W2 is equal to 0.5 times W1, and L2 should be equal to L1. If this is true, then delta Q2 will be equal to delta Q1. Thus, we can say that here the condition is W2 should be equal to 0.5 W1 and L2 should be equal to L1. However, unfortunately, the assumption that we have considered of equal splitting of the charges between source and drain is generally invalid, and that makes this approach less attractive. However, there's one more interesting thing is that if we choose W2 is equal to 0.5 times W1 and L2 to be equal to L1, then the effect of clock feed through is by default suppressed. So this is shown in this figure. That is, there is a clock Ck, it is coupled between the gate and the source, and obviously there will be a coupling of the clock Ck bar for the dummy switch between gate and the source and the gate and the drain. So there is a common point, that is at V out, and we draw the entire clock network. So the total charge V out is going to be 0. In V out is going to be 0 because in this case this will contribute the charge, that is M1. It will generate a voltage and the total value is equal to minus Vck W1 COV upon W1 COV plus CH plus 2 W2 COV. Second will be Vck 2 W2 COV upon W1 COV plus CH plus 2 W2 COV, and this will be equal to 0. That means dummy switch, it basically reduces the charge injection. Another approach to lower the effect of charge injection is to incorporate both PMOS and NMOS devices. So PMOS devices will produce delta Q because of the electrons, and NMOS devices will produce delta Q because of the electrons, and PMOS devices will produce delta Q because of the holes. And both these switches turns off simultaneously, and hence the equal amount of charges of opposite type will lead towards the same node, that is V out. So the opposite charge packets injected by the two cancel each other. Thus, delta Q1 to cancel delta Q2, we must have W1 L1 C0x Vck minus Vin minus Vth of NMOS is equal to W2 L2 C0x Vin minus Vth of PMOS. Thus, the cancellation occurs for only one input level. Even for the clock feed through, the circuit does not provide complete cancellation because the gate drain overlap capacitance of NFET is not equal to PFET in this case. We also have the knowledge of the differential circuits. So why not to use the differential circuits for the cancellation of these charges? So in this case, what we do is we use two circuits. That is, top one is duplicated at the bottom, and we have the differential inputs available right now with us, and we will have the differential output also. So the V in 1 generates charges delta Q1, and V in 2 generates charges, that is channel charges, delta Q2. So if you assume that delta Q1 is nearly equal to delta Q2, then definitely delta Q1 minus delta Q2, if you simplify this, you will get it equal to 0. In other words, the overall error is not suppressed for the differential signals. Nevertheless, this technique both removes the constant offset and lowers the nonlinear component at least, if you can observe the final equation. The characteristics for this circuit exhibits no offset. If you also observe, then nonlinearity of the body effect now appears in both the square root terms, in first as well as second square root term, leading to only the odd order of the distortion. The problem of the charge injection continues to limit the speed precision envelope in the sample data systems. Many cancellation techniques have been introduced, but each leads to the other trade-off, which we have to understand. Now let us study the switch capacitor amplifier circuits. So what we have studied up till now is that what exactly the sample circuits, what is the motivation behind going for the sample circuits, then what is sample hold circuit and what is an amplifier. Then what we have discussed is the speed considerations for these switches, whether we should go for NMOS, PMOS or a transmission gated switch. We have identified their limitations, etc. Then we have gone for the precision considerations of the switches. With this background, now we have to design various switch capacitor circuits. So let us first consider a unity gain sampler. So this is the circuit which we call it as a unity gain amplifier. So first part is basically a buffer and it's a continuous time. We want it to be used as a discrete time, and hence we connect a sample and hold circuit at the input. So basically right hand side circuit is the sample and hold circuit, or you can call it as a sampling circuit followed by unity gain buffer. So for the earlier circuit, that is this, the input dependent charge injected by S1 onto capacitor CH, it basically limits the accuracy. So to have more accurate sampling, what we do is we go for the next circuit which is shown in this figure, where three switches S1, S2 and S3 control the sampling and the amplification mode. In the sampling mode, S1 and S2 are on and S3 is off. What it yields is the next circuitry, that is sampling circuit. And we open S1 and S2 and we close S3, then what we get is the holding circuit. Now in sampling circuit, Vout is equal to Vx is equal to 0, and the voltage across capacitor primarily tracks the input voltage Vin. So you can say that at time t equal to t0, when V input is equal to V0, that is shown in this figure, and S2 turns off and ST turns on, placing the capacitor around the op amp and turning the circuit into an amplification mode. The op amp's high gain requires that the node X still be a virtual ground. And since the charge on the capacitor must be conserved, V output rises to a value approximately equal to V0. And this voltage is therefore frozen and it can be processed by the subsequent stages. With the proper timing, the problem of channel charge injection can be easily alleviated in this circuit. So when S2 turns off slightly before S1 does, let us consider a situation where S2 turns off slightly before S1 does. So it will introduce the charges at the node X, and those charges are indicated here by delta Q2, and obviously it will produce an error delta Q2 by CH. However, this charge is quite independent of the input level because node X is a virtual ground. For example, if S2 is realized by an NMOS switch whose gate voltage is equal to VCK, then delta Q2 will obviously be equal to WLC0X VCK minus VTH minus Vx. Although the body effect makes VTH a function of Vx, delta Q2 is relatively constant because Vx is quite independent of the input voltage. The constant magnitude of delta Q means that channel charge of S2 introduces only an offset rather than gain error or non-linearity in the input-output characteristics. However, charge injection by S1 introduces no error if S2 turns off first. So after the S2 turns off, node X floats, maintaining a constant total charge regardless of the transitions at the other nodes of the circuit. As a result, after the feedback configuration is formed, the output voltage is not influenced by the charge injection due to S1. From another perspective, we can say that node X is a virtual ground at the moment S2 turns off, which freezes the instantaneous input level across CH and yielding a charge equal to V0CH on the left plate of CH. After settling with the feedback, node X is again a virtual ground, forcing CH to still vary VOCH, and hence the output voltage to be approximately equal to V0. So what this figure shows is that effect of charge injected by S1. So charge injection of S1 introduces primarily no error. However, the condition is S2 should turn off first. Thus, it is very important to synchronize these switches. So S2 should turn off first. Therefore, this clock will ensure that S2 turns off first. Then we have introduced two inverters over here, so which will ensure that once S2 turns off, after some time S1 will turn off, and when these two turns off, after that S32 should turn on. So that has been ensured by this third inverter. So this circuit shows the generation of the proper clock edges for the unity gain buffer circuit. We can also realize the unity gain buffer by using a differential configuration, which is shown in this figure. So here SQ is used for equalizing the charge at node X and Y if at all the charge injection happens because of the switches S2 and S2 dash. So this SEQ is going to be turned off slightly after S2 and S2 dash turns off and before S1 and S1 dash. Now let us consider the precision considerations for this unity gain amplifier. So this is the input capacitance, which you can call it as a parasitic capacitance at the input of the amplifier, and this is the network in the amplification mode. And now we write the equation for this network, that is V output is equal to minus CH V naught plus C in Vx upon CH, that is voltage across capacitor is nothing but CH V naught plus C in Vx, and this is equal to Vx, correct? Or you can also say V out minus Vx is equal to the voltage across the capacitor, that is given by this formula. So here Vx is equal to minus V out by AV, or you can say for operational amplifier V out is equal to minus Vx is the input times gain of the different open loop amplifier, that is AV1. So you substitute this value over here, you get V out is equal to V0 upon 1 plus 1 by AV into C in by CH plus 1. So we can approximate this term by taking in the numerator as V out nearly equal to 1 minus 1 by AV1 C upon CH plus 1. What it shows is that V output will be equal to V0, and there will also be an gain error which is given by 1 by AV1 into C in by CH plus 1. So if we have V in very much less as compared to CH, which is an obvious, then we get V out is equal to V0 upon 1 plus AV inverse. So this suggests that the input capacitance must be minimized even if the speed is not critical. Now let us study speed considerations for this circuit. So for speed considerations, basically we want the total resistance and the capacitance. So we convert this network into an equivalent network, or we draw its Thevenin's equivalent. So here this is the node X at which input is applied to the op amp, and there is a GMVX. There is an R on the resistance of the switch, and we are interested into the impedance at node X. So we connect Vx and we allow current Ix to flow through it, and R out is the output resistance of the amplifier. Thus for this network we can say that Vx voltage is equal to Ix minus GMVx times R0, that means voltage drop across R0, plus voltage drop into the R-on. Vx is voltage drop into the R-on plus voltage drop into the R0. Voltage drop on R-on is Ix into R-on, and voltage drop in R0 is Ix minus this current, that is GMVx times R0. So what is Rx? Rx is R0 plus R-on upon 1 plus Gm times R0, correct? So typically R-on, that is on resistance of the switch, will definitely be very less as compared to the output resistance of the operational amplifier, that is R0. That means Gm R0 will be very high as compared to 1, and therefore what you get is Rx, that is Vx by Ix over here, it will be nearly equal to 1 by Gm. Thus sampling time you can say is resistance of the switch 1 plus Rx, that is 1 by Gm, into the holding capacitor Ch. Now let us consider the circuit as it enters into the amplification mode. As shown in this figure, along with the both op-amp input capacitance and the load capacitance, the circuit must begin with output voltage equal to 0 and eventually produce Vout is equal to V0. If the Cin is relatively small, we can assume that the voltage across Cl and Ch do not change instantaneously, concluding that if Vout is nearly equal to 0, Vch is equal to V0 and Vx will be equal to minus V0 at the beginning of the amplification mode. In other words, the input difference sensed by the op-amp initially jumps to a large value, possibly causing the op-amp to slew. But let us first assume the op-amp can be modeled by a linear model and determine the output response. So to simplify the analysis, we represent the charge on capacitance Ch by an explicitly series voltage source Vs, which is shown in the bottom figure, that goes from 0 to V0 at t equal to t0, while Ch carries no charge itself. So the objective is to obtain the transfer function Vout upon Vs for this network and hence the step response. So for this circuit, now write down the equations. So the equation will be Vout is 1 by R0 plus CLS plus GMVX is equal to Vx plus Vx minus Vout times CHS. Now since the current through capacitor Cin is equal to Vx Cin as, you can write Vx Cin as upon CHS plus Vs is equal to Vout. Now substitute this value over here and simplify the equation, and we also have it typically Gm R0 Ch greater than Ch. So finally you get the time constant in the amplification mode as Cl Cin plus Cin Ch plus Cs Cl upon Gm Ch. And what this equation tells you is that time constant in the amplification mode, it primarily depends on the capacitances and is independent of the op-amp output resistance. This is because higher R0 leads to a greater loop gain and it eventually yields a constant closed loop speed. So if input capacitance is very less as compared to Cl, Ch, then this equation it reduces only to Cl upon Gm, which is an expected result because with negligibly small value of Cin, the output resistance of the unity gain buffer is equal to 1 by Gm. Now let us study the sleeving behavior of the circuit, and let us consider a telescopic operational amplifier as an example. So here this entire network shown is a telescopic operational amplifier, and we have connected the output Vout to a Vx via the holding capacitor Ch. What does it mean? That means that this is circuit shown is in an amplification mode. So upon entering the amplification mode, the circuit may experience a last step at the inverting input. The tail current of the op-amp's input differential pair is then steered to one side and its mirror current charges the capacitance Cin at the output. Since M2 is off during the sleeving, C in capacitance is negligible and the slew rate is approximately equal to ISS by CL. The slewing continues until Vx is sufficiently close to the gate voltage M1, after which point the settling progresses with the time constant which we have derived in the earlier slide. Thus, we can say that input capacitance of the op-amp degrades both the speed and the precision of the unity gain sampler. For this reason, we can use the bottom plate of the capacitor, which is usually driven by the input signal, which is shown in the right hand side figure. Or we can say that the output of the op-amp and the top plate is connected to node X. This minimizes the parasitic capacitance seen from the node X to the ground. This technique is called as bottom plate sampling. Basically, driving the bottom plate by the input, or you can say the output, avoids the injection of substrate noise to ground or substrate noise to node X. Now this is the non-inverting amplifier, and now let us try to focus on the non-inverting amplifier circuit. So in case of non-inverting amplifier, we have here operational amplifier. There are two capacitances C1, C2, and there are three switches. So obviously we will have S1, S2 as a closed switch when we want to sample the input, and we will open S3. So you will get this second network, and when you want the amplification mode, obviously you will open S1 and S2 and you will close S3. So you get this second network, correct? So in this case, C1 will charge to V in C1, and then those charges will be transferred to C2. So it will produce the voltage as charge upon capacitance, that is C1 V in upon C2. As with the unity gain circuit, the non-inverting amplifier avoids input dependent charge injection by proper timing, that is turning S2 off before S1. After S2 is off, the total charge at node X remains constant, making the circuit insensitive to charge injection of S1 or charge absorption of S3. Let us first study the effect of S1 carefully. As shown in this bottom figure, the charge injected by S1, that is delta Q1, changes the voltage at node P approximately by delta Vp, which is equal to delta Q1 by C1, and hence the output voltage minus delta Q1 by C2. However, after S3 turns on, Vp drops to 0. Thus, the overall change in Vp is equal to 0 minus V in, which is equal to minus V in 0. It produces an overall change in the output voltage, which is equal to V in 0 C1 by C2. The key point here is that Vp goes from a fixed voltage V0 to another to 0 with an intermediate perturbation due to S1. Since the output voltage of interest is measured after the node P is connected to ground, the charge injected by S1 does not affect the final output. From another perspective, we can say that the charge on the right plate of C1 at instance S2 turns off is approximately equal to minus V in 0 C1. Also, the total charge at node X must remain constant after S2 turns off. Thus, when node P is connected to ground and the circuit settles, the voltage across C1 and hence its charge are nearly zero. In other words, the output voltage is approximately equal to V in 0 C1 by C2, regardless of the intermediate excursions at node P. Now, similar to the buffer circuit, we study over here the precision considerations and the speed considerations for the non-inverting amplifier. Thus, you consider the non-inverting amplifier, which is shown in this figure, and in this case input capacitance is also shown. For this network, calculate the V out by V in. Thus finally you get V out by V in as C1 by C2, 1 minus C1 C2, CO2 plus C1 plus C in upon C2 into 1 upon AV1. You can observe from this equation that there is a gain error of C2 plus C1 plus C in upon C2 times AV1. The gain error increases with the nominal gain, that is C1 by C2. So the numerical over here is that for the given circuit, C1, C in and AV are already provided. What is the maximum nominal gain? C1 by C2. And the circuit can provide with a gain error of 1%. So gain error is given by C2 upon C1 plus C in upon C2 AV1. So you substitute all the values, you get 0.01. So you simplify this equation. Finally, you will have C1 by C2, which is nominal gain, which is equal to 8. Now let us identify the speed considerations. So this is the equivalent circuit in the amplification mode for non-inverting amplifier. Here V in, C1 and C in are shown. Now we derive the equation for the transfer function for this network using the earlier method, and this is what we get with a overall time constant tau amplification is equal to CLC equivalent plus CLC2 plus C equivalent C2 upon GMC2. What it tells you is that there is a direct dependence of tau amplification mode upon the nominal gain C1 by C2. So if you consider a special case, that is CL equal to 0, then you get tau amplification as C1 plus C in upon GM, that is, it is independent of the feedback capacitor. Now let us consider the last circuit, that is switch capacitor integrator. So right hand side figure is the continuous time integrator where there is a feedback capacitor CF and the input resistance R1. Thus in this case output voltage V out is given by minus 1 upon RC integral of V in dt. So for sample data circuits, we have to replace this resistor by discrete time counterpart. So let us first study the function of a basic resistor. So in this figure, resistor is connected between node A and B and it carries current I. So basically, what is the function of this resistor? So resistor is used to transfer the charges from node A to node B with respect to time. Thus you can say that when you apply VA to node A, this VA should be transferred to node B, so it will make it as VB. So the current flowing through resistance, that is I, will be equal to VA minus VB upon R. Can we perform this activity, that is, take a certain amount of charge from node A and give it to node B by a capacitor along with some switches? So that is shown in the right hand side figure. So here there are two switches, S1, S2, and there is a capacitor CS. So when S1 is closed, S2 is open. So capacitor CS will charge to VA, and then we will open the S1 and close S2. So CS charges will be transferred to VB. So what is the formula for current through AB here? It is nothing but C dV by dt, that means CS, derivative of voltage at A minus voltage at B upon dt. So 1 upon dt is nothing but FCK. Thus we can write current IAB through this network will be equal to CS FCK VA minus VB. If you compare it with the continuous time resistor, we can say that resistance is nothing but, for this network, there is an equivalent resistance, is nothing but 1 upon CS FCK. That means by changing the clock frequency, that is switching frequency of the switch, we can get the variable resistor. Thus this concept is used in the switch capacitor integrator. So this circuit is called as a discrete time integrator, and this is the response of the discrete time integrator. So when you apply the input, or close the switch S1, open the switch S2, C1 will charge to Vin, and when you open switch S1 and close S2, C1 is connected to the amplification mode, so you get an integrated waveform. Therefore output voltage will be equal to Vout k minus 1 Tk minus Vin k minus 1 Tck into C1 by C2 after every clock cycle. And in this case we have assumed that the gain of the operational amplifier is large. However, this integrator suffers from two important drawbacks. First, the input dependent charge injection of S1 introduces non-linearity in the charge stored on C1 and hence the output voltage. And second is that non-linear capacitance at node P resulting from source drain junctions of S1 and S2 leads to a non-linear charge to voltage conversion when C1 is switched to node X. Therefore, this is our modified circuit. So this circuit is, we can call it as an integrator, which is a parasitic insensitive. In this case, switch S1 and S3, when it is on, it is in a sampling mode, and when S2 and S4 is on, it is in an integrating mode. So the figure B is for the sampling mode, figure C is for the integrating mode. Since left plate of C1 is driven, the charge injection or absorption of S1 or S2 contributes to no error, and it removes the non-linearity. So thank you very much.